Hello and welcome back to Calculus 1. This is section 5.4 on working with integrals, working with definite integrals. So we already seen some of the formulas for these definite integrals. Primarily the one that says if you go from a to a, well, I can write them down. Definite integral from a to a of whatever function you plug in here, it's going to be 0. If you swap the limits to b to a, then you will pick up a negative in front of the integral. And then lastly, that you can break the interval anywhere. So go from a to c, f of x dx plus c to b, f of x dx. So all of these formulas were in 5.2, which is where we learned about the definite integral. And there was also the formula, which was now labeled as Fundamental Theorem of Calculus Part 1, which teaches you how to integrate and put the, plus c and all of that stuff. I mean, not put plus c, calculate the limits. Now, what we are working on today in 5.4 is the just few formulas that are quality of life formulas. We don't really need them, but it's cool to simplify and make calculations easier if you spot that you can use them. And in order for that to work, we need to review some of the old pre-calculus stuff. So in pre-calculus 1, you learn about even and odd functions. So for odd functions, we have the way to test, and that is that f of negative x needs to be negative f of x. So what would be the example? Say f of x is equal to x cubed minus 6x to the 7. If you have that, then you will try and figure out what's f of negative x. That's going to be negative x cubed minus 6 times negative x to the 7th power. And if you do this, you will get negative x cubed, because you have 3 negative signs, right? The negative is grouped with x. So you have negative x times negative x times negative x. So you have 3 negatives, so negative remains, and you have x cubed. And you have 7 negative signs for x to the 7, negative x to the 7, so this becomes plus 6x to the 7. But if you carefully observe there, and you can pull minus outside to make it x cubed minus 6x to the 7, which is the original problem. So this is equal to negative f of x. So this calculation helped us prove in pre-calc 1, this calculation helped us prove that the function is odd, because we used the test for odd functions. Even functions have the property that f of negative x is the same as just the base f of x. And let's say you have f of x to be given as 3 minus x squared plus x to the 8 or something, or well, x to the 8, fine. So now when you compute f of minus x, you get 3 minus negative x squared plus negative x to the 8. That would be 3 minus x squared plus x to the 8, because now you have even amount of minus signs and they will always multiply into plus, which is, as you can see, f of x. Now what you want to maybe make a connection here is look at the exponents. For odd functions, all of the exponents are odd, and for even functions, all of the exponents are even. Now a lot of this stuff will be falling in place in Calc 2. Right now we don't have to worry about the proofs. We just remember that even trig would be cosine x and secant x, and the odd trig functions are sine x, tangent x, cosecant x, and cotangent x. So we have 2 evens and 4 odd trig functions. The proofs that these are even and odd will be found in Calculus 2 when you finish chapter 9. It's the last section of chapter 9. Now, what do we gain in integration if we know that the function is even or odd? Well, we have these formulas now. Integral from negative a to positive a of f of x dx when this is even, when function is even, is equal to 2 times the integral 0 to a of f of x dx. So what we have achieved is that we don't have to compute at negative a anymore. We can just compute at positive, we can compute at 0 and double the entire integral. So what is the idea of this? So let's say you have cosine function. Cosine function will go through 1, fall down to pi over 2, there's another one over here, negative pi over 2, and so on. So if you are on the symmetric interval, meaning look, a is equal to a, just one is negative, so this is your negative a and positive a. Wouldn't you agree that this part doubled will give me the other side, and that's all of the area? So that's the idea of this. Times 2. So this is the main formula for us. And then we have another one. Negative a to a of f of x dx when f of x is odd. And the answer is always 0, because it cancels out. Good example would be a sine function, because we already did this one in class. Did it wrong. There we go. So if you pick your negative a to be here and your positive a must be there, then these two areas are exactly the same and they subtract to 0, because one is below x-axis and there is nothing there, so the value is 0. Does that mean the area is 0? No. For area you have to use absolute values and break it. You can break it at 0, so go negative a to 0 and then 0 to a. So yeah, there are ways to figure out the area. But now, all we are claiming is the quality of life improvement here is that if you have odd function, you don't actually have to bother computing the integral at all. It's just done, right, immediately. So I'm going to give you an example. Ooh. Wow. That sound. Integral from negative pi to positive pi of sine x plus cosine x dx. Try this real quick. So hopefully you're not integrating and plugging in, because what you can do is use the rule that allows you to split this into two integrals. And you are on a symmetric interval. So this is odd. And this is even. So this one is 0. And this one is 2 times integral 0 to pi cosine x dx. And that's much easier to compute. So integral of cosine is negative sine x. And then you have a 2 in front. Yeah, this looks bad. So I just want to put negative 2 sine There we go. And then we have the calculation from 0 to pi. So sine of pi is 0, sine of 0 is 0, so it's a big fat 0 too. So the whole integral is equal to 0. Unless they're looking for area. If they're looking for area, then you would have to break this sign into, you have to break the cosine over there. That is 0 to pi. You have to break it into 0 to pi over 2, and then pi over 2 to, right, and make the second one in the absolute values. I have a lot of cool problems. Give up problem 11 through 24. Anyone? Just pick a number, 11 to 24.
23.
23 it is. Okay.
Oh God, no.
Don't worry about it.
Okay.
We got this. X cubed minus 4x divided by x squared plus 1 dx. So what now? Equal to 0, done, right? Odd on top, even on the bottom, and see, you have the situation of tangent x is equal to sine x over cosine x, right? That's odd, that's even, and the result is odd, right? So you have the same thing, odd, even. So the result of this would be, I mean, look, when you divide x cubed by x squared, what do you get? You get x. What's the power on x? 1, right? So you are going to get odd function there. You're on a symmetric interval, so odd function on a symmetric interval is equal to 0. And that's that. The last part of this lecture is the average value formula, which is also known as the mean value theorem for integrals. So average value. What do we have on average value? F bar is equal to 1 over b minus a integral a to b f of x dx. So this is our average value formula. What it does is it makes the areas the same. So you would draw, so let's say from A to B. So there will be a line somewhere over here. Nah. somewhere over there, that will cut that would take this part of the line on top and provide the average for it. This is the average value of the function. We have problems we can solve. I mean, this is just, you plug stuff in the calculator and, not the calculator, in the integral and calculate. So let's see, the homework says calculate the, so problem 26 gives you the formula x squared plus 1 on negative 2 to 2. That's what we have. So please plug in. So all you need to do is to plug in, right? Average value is 1 over 2 minus, we have negative 2, integral negative 2 to 2 of x squared plus 1 dx. Do you guys see that this is actually even? So we can use our trick. 2 times the integral from 0 to 2. So we are reducing calculations, which is great. This now becomes 1/2 x cubed over 3 plus x from 0 to 2. That's 1/2 plug in 2. That's 8/3. Oops. Plus 2. 2, 6, 14. Well, half of 8, that's 4/3 plus 1. So 7/3. That was that. And now at the end, we're just going to rename this into the mean value theorem for integrals. Mean value theorem for integrals. So let f be continuous on closed interval a b. There exists a point C in AB such that, and now we have f of C equal to 1 over b minus a integral a to b f of x dx, which is actually your f bar. So mean value theorem for integrals. And as you can see, all you need to do is to compute the regular x bar integral. And then you can compute C. Let's go find the problem. So problem 44 says f of x, well, let's start with the find C. For f of x equals 1 over 4 on, no, 1 over x on the interval 1 to 4. We have f of c is equal to 1 over b minus a integral a to b f of x dx. Now plug everything in. F of c, well, that's 1 over c, right? Because f of x is 1 over x, then f of c is 1 over c. On the other side, we have 1 over 4 minus 1, b minus a, integral 1 to 4, again, a and b, and then you have 1 over x dx. So 1 over c is equal to what? Well, that's 1/3. And what's the integral of 1 over x? What's the integral of 1 over x? See, I'll have to include this on the test. ln, very good. So this is ln absolute x computed from 1 to 4. So 1 over c is equal to 1/3 ln 4 minus ln 1. Now we all know that ln 1 is 0, right? So we don't have to worry about that. So now what I have is 1 over c is equal to ln 4 over 3. From where, when you flip the left side, you flip the right side, and there is your answer. That's it. Bye.